Earth's protective blanket, the atmosphere. This thin veil of gases is what makes life on our planet possible. Our planet Earth is enveloped in a delicate life-sustaining layer of gas we call the atmosphere. This protective layer is composed of nitrogen, oxygen, and trace amounts of other gases, creating a perfect balance for sustaining life. This gaseous shield protects us from the harsh realities of space like incoming meteoroids and harmful solar radiation. Without it, the surface of our planet would be bombarded by space debris and exposed to deadly levels of ultraviolet radiation. It's the very reason we can breathe, experience weather, and witness stunning sunsets. The atmosphere plays a crucial role in regulating our climate and weather patterns, making Earth a dynamic and ever-changing environment. Without the atmosphere, Earth would be a barren, lifeless rock, much like our moon. The moon, lacking an atmosphere, is a stark reminder of how vital this layer is for sustaining life. The atmosphere is not uniform. It is a complex system with varying temperatures, pressures, and compositions at different altitudes. It is divided into distinct layers stacked upon each other, each with unique properties and characteristics. These layers interact in complex ways to support life and protect the planet. These layers, starting from the Earth's surface, are the troposphere, stratosphere, mesosphere, thermosphere, and exosphere. Each layer has its own role in maintaining the balance of our planet's environment. Today we journey into the second layer, the mysterious and crucial stratosphere. This layer, located above the troposphere, is where the ozone layer resides, protecting us from the sun's harmful ultraviolet rays. The stratosphere is also where commercial jets fly, taking advantage of its stable conditions. Join us as we explore the wonders and significance of the stratosphere in our next segment. Imagine embarking on a hot air balloon ride straight up from the Earth's surface. You would first travel through the troposphere, the layer where most of Earth's weather occurs. It's a turbulent zone of churning air masses, clouds, and precipitation. As your balloon ascends higher, you would leave behind the familiar sights and sounds of the troposphere and enter a new realm, the stratosphere. This layer, extending from about 10 to 50 kilometers above the Earth's surface, is a place of unexpected warmth, minimal turbulence, and a crucial layer for life on Earth. The stratosphere is often referred to as Earth's sunscreen due to the presence of the ozone layer. This layer, situated within the stratosphere, acts as a shield against harmful ultraviolet, UV, radiation from the sun. UV radiation is a form of energy that can be harmful to life, causing sunburns, skin cancer, and eye damage. The ozone layer absorbs most of the sun's harmful UV radiation, allowing only a small, less damaging portion to reach the Earth's surface. Without the ozone layer, life on Earth as we know it would be impossible. One of the most intriguing aspects of the stratosphere is its temperature profile. Unlike the troposphere, where temperature decreases with altitude, the stratosphere experiences a temperature inversion. This means that temperatures increase as you go higher. At the bottom of the stratosphere, temperatures are frigid, averaging around -55 degrees Celsius or -67 degrees Fahrenheit. However, as you ascend higher, temperatures gradually rise, reaching a balmy 0 degrees Celsius or 32 degrees Fahrenheit at the stratopause, the boundary between the stratosphere and the mesosphere. Section 5. Why temperature increases with altitude in the stratosphere. The reason for this temperature inversion lies in the ozone layer's interaction with solar radiation. As we learned earlier, the ozone layer absorbs most of the sun's harmful UV radiation. This absorption process converts UV radiation into heat, warming the surrounding air. Since the ozone layer is concentrated in the upper stratosphere, this region receives the most direct solar radiation and experiences the most significant heating. Consequently, temperatures increase with altitude in the stratosphere, creating a stable and stratified layer. Section 6. Calm and stable. Ideal for aviation. The stratosphere's stable and predictable conditions make it ideal for long-distance air travel. Commercial airplanes often cruise in the lower stratosphere, above the turbulent weather patterns of the troposphere. The lack of clouds and precipitation combined with the stable air allows for smoother flights, reduced turbulence, and improved fuel efficiency. Passengers can enjoy a more comfortable flight while airlines benefit from lower operating costs. Section 7. Jet streams, rivers of wind in the stratosphere. While the stratosphere is generally calm, it is also home to jet streams, fast-flowing, narrow air currents that encircle the Earth at high altitudes. These powerful winds, reaching speeds of up to 200 miles per hour, flow from west to east in a wavy pattern. Jet streams play a crucial role in weather patterns, influencing the movement of air masses in storms. Pilots often take advantage of jet streams to reduce flight times and fuel consumption. Section 8. Ozone layer, Earth's protective shield. As we've learned, the ozone layer, a region of high ozone concentration within the stratosphere, is vital for life on Earth. Ozone, a molecule made up of 3 oxygen atoms, acts as a natural filter for harmful UV radiation from the sun. When UV radiation strikes an ozone molecule, it is absorbed, and the ozone molecule splits into an oxygen molecule and a single oxygen atom. This single oxygen atom can then recombine with an oxygen molecule to form ozone, completing the ozone-oxygen cycle. Section 9. The ozone hole, a threat to life. The ozone layer, a fragile shield of gas, protects life on Earth from the sun's harmful ultraviolet, UV radiation. Without it, the planet would be exposed to dangerous levels of UV rays, which can cause severe health and environmental issues. Unfortunately, human activities, particularly the release of man-made chemicals like chlorofluorocarbons, have depleted the ozone layer, particularly over Antarctica. These chemicals, once released into the atmosphere, undergo complex chemical reactions that result in the breakdown of ozone molecules. This process is exacerbated by the extreme cold temperatures in the polar stratosphere, leading to the formation of the infamous ozone hole. CFCs, once widely used in refrigerants, aerosols, and other industrial applications, rise into the stratosphere and break down ozone molecules, weakening Earth's protective shield. The stability and longevity of these compounds mean they can persist in the atmosphere for decades, continuing to cause damage long after their initial release. This has had a profound impact on the ozone layer, particularly in the polar regions. This depletion, known as the ozone hole, allows more harmful UV radiation to reach the Earth's surface, increasing the risk of skin cancer, cataracts, and other health problems. UV radiation can also harm marine ecosystems, affecting plankton and other organisms at the base of the food chain, and can damage crops, reducing agricultural productivity. International agreements, such as the Montreal Protocol, have phased out the production of ozone-depleting substances, leading to a slow but steady recovery of the ozone layer. The Montreal Protocol, signed in 1987, is considered one of the most successful environmental treaties with widespread global cooperation. Scientists continue to monitor the ozone layer, and while recovery is ongoing, it serves as a reminder of the impact human activities can have on the planet and the importance of international collaboration in addressing global environmental challenges. Section 10. Importance of the stratosphere, more than just a layer. The stratosphere, though seemingly distant and serene, plays a vital role in sustaining life on Earth. Its unique characteristics, from temperature inversion to the ozone layer, make it a crucial component of Earth's atmospheric system. Understanding the stratosphere and the processes that occur within it is essential for comprehending Earth's climate, weather patterns, and the delicate balance of our planet's life support system. Section 11. Fun fact: the highest skydive. In 2012, Austrian skydiver Felix Baumgartner made history by jumping from a helium balloon in the stratosphere from a staggering altitude of 39 kilometers above Earth's surface. This jump was not just a leap of faith, but a meticulously planned mission. Baumgartner's daring feat, part of the Red Bull Stratos project, showcased the extreme conditions of the stratosphere. The project aimed to transcend human limits and push the boundaries of skydiving. The technological advancements that allow humans to explore these previously unreachable heights were crucial. The team developed specialized suits and equipment to withstand the harsh conditions of the stratosphere. His jump provided valuable scientific data about the human body's response to extreme altitude and supersonic speeds. This data is invaluable for future space exploration and high-altitude missions. As he became the first person to break the sound barrier without vehicular power during freefall, Baumgartner's achievement was a milestone in both aviation and human endurance. His supersonic freefall reached speeds of over 1,357.64 kilometers per hour, demonstrating the incredible potential of human capability when combined with cutting-edge technology. The success of the Red Bull Stratos project not only inspired millions around the world, but also paved the way for future high-altitude endeavors. Felix Baumgartner's highest skydive remains a testament to human courage, innovation, and the relentless pursuit of pushing boundaries.